next week. The quiz is going to be about mixtures and solutions and gases, gas laws. Let's begin. Which of the following is a heterogeneous mixture? A heterogeneous mixture is a mixture that has more than one appearance, more than one appearance. So you can see clearly the components of the mixture or some of the components of the mixture. So salt, water, air, salad dressing, and vinegar. Salt water, the salt disappears, it dissolves in water, so you cannot see them because the particles are very small. The air is a mixture of of gases like oxygen, nitrogen, carbon dioxide. All of these are colorless gases, so you cannot see them. And vinegar is acetic acid mixed with water, so it's well mixed. You cannot see which one is the vinegar and which one is the water. However, the salad dressing, you can see the lettuce, you can see the cucumber, the components and the ingredients of the salads are very well appearing. Now, here again, I'm going to distinguish between a homogeneous and heterogeneous mixture. A homogeneous mixture, also known as solution. A heterogeneous mixture, we have two types, which I will discuss later on. You have the suspension and you have the colloid. However, in general, heterogeneous and homogeneous mixture. The heterogeneous mixture is a as a definition, is a non-uniform mixture where you can see clearly the components, where you can see the components. So they're large enough to be seen, like sand in water. Whereas in homogeneous mixture, it's a uniform mixture, um, and you cannot see the components. The components are very small that can't be seen without a microscope. Okay, moving on. In sugar solution, which component is the solute? Here, there's a next question differentiating between solute, solvent, and solution. Now, I'm just going to answer. In sugar solution means I have sugar, I put it inside water. So the sugar is the one that's going to dissolve because it's the one in less quantity. So the solute is the sugar and water is the solvent. What's the difference between solute, solvent, and solution? So solute is the substance that is dissolved. The substance that will dissolve in solvent. The solvent is the substance that's going to dissolve the solute. The substance in larger quantity, more than solute. If it's hard to know which one is solute and which one is solvent, we just compare the amounts. The one that has more amount is the solvent, and the one that has less amount is the solute. So that's why I'm writing here more than solute for the solvent. Okay, in which the solute will dissolve. Together, they form a solution. So once dissolved, the solute and the solvent, they form a solution. Once dissolved, the solute and solvent together have a uniform composition and form a solution. I hope that this is clear. Give examples of each. So, for example, uh, for the solute, I can take copper sulfate or salt or sugar. Um, I can, yeah, so this is sugar, water, sweet water is the solution. Sugary water, sweet water. Okay? Next, which is an example of a gas-gas solution. It means that the solute and the solvent are both gases. The best example to this is the air, which is composed of many gases. The solvent in the air is the nitrogen, and the solute is oxygen, carbon dioxide, hydrogen, helium, argon, all the other colorless, unseen gases. But the one in larger quantity is the nitrogen. So this is the solution of air. This table is very important, and we need to know all the examples. Whenever you are asked to give an example of a solution, you need to know what's the type of solute and solvent. So gas and gas, just like the one that I give. First, think of the example, and then you can decide the phase of the solute and the solvent. So the air is the other gases in nitrogen, or oxygen in nitrogen. So nitrogen is the one in larger quantity, which is gas, and oxygen, for example, is in less quantity, which is the solute. Gas in liquid. Take the simple, easy examples. The sparkling water, any sparkling drinks, fizzy drinks. Okay, so let's say fizzy drinks or soda. Okay, so what does it have? This one, it has carbon dioxide in water. So the solute is the carbon dioxide, which is a gas dissolved in water, the H2O, which is a liquid. Liquid in liquid. There are a lot of examples, liquid in liquid. The best and simple example is vinegar. Anything you can mix with water, acetone, vinegar, alcohol. All of these are examples that we were discussing in class. So here I'm going to write vinegar, which is acid. Acetic acid is the vinegar in water. Acetic acid in water. So both of them are liquid. The solvent again is the water, and the solute is the acetic acid. Solid in liquid. Any solid solute you dissolve, and it can dissolve easily, like salt in water, sugar in water. Any powder, when you make juice, it's solid solute, copper sulfate in water. Let me write this. Copper sulfate. Wait, I'll write it. Copper sulfate solution, which is CuSO4 in water. So again, the water is the solvent, which is liquid, and the copper sulfate is a blue solid crystal. So it's solid. Solid in solid. Whenever we say solid in solid, think about alloys, brass, steel, bronze. So let me take an example. Steel, which is made up of um, iron and carbon. So basically, it is carbon in less quantities in iron, or brass. Another example. The zinc is the one that has less quantity. It's zinc in copper. Uh, there's a lot. So I'm just gonna give you one more example of alloy. Let me just 1 second. Um, we can have just bronze. It's copper in tin. So bronze, because these are well known, bronze, it's copper in tin. So all of these are solid, solid, solid. Now, let me just take the example of brass, because I need to specify which alloy I'm talking about in order to choose the solute and the solvent. So in brass, it is the zinc solute and copper solvent, the one in larger quantity. Gas in solid, and this is the amalgam, the one that we put in dental, you know, the filling, in dental filling. Or another example, gas. No, the other one, this is liquid and solid. Wait, I didn't mention liquid and solid. Liquid in solid. Liquid and solid is the amalgam. Not 1 second. Let me just. Yes, the dental amalgam. I'm not wrong. So we call it here the dental amalgam. This is the one. You have mercury as a solute. We have the mercury, which is a liquid solid, in silver. Okay, and silver, tin, and other metals. We dissolve it in silver. Okay, now for the gas in solid, I'm gonna give you a good example. Um, gas in solid solutions, it's hydrogen gas in palladium. Palladium is the solid, and hydrogen is the gas. Can't think of other examples. Let me just check something if I can find more Simple examples. So gas and solid. It's the hydrogen peroxide. There are barely examples online for this one. Let's just stick to this one example since that's the only one they've given us. Gas and solid type. Let's continue. I don't want to waste the time. Which mixture? Which mixture type shows the Tyndall effect and does not separate upon standing? Okay, here's the part where I will explain the difference between these three type of mixtures. Okay, now Tyndall effect is a test that we do with light where we direct a beam of light toward a mixture. If this mixture scatters light, it means the particles appear, the particles of the mixture inside appears when the light goes through them. We say the word, we say scatter light. And the one that scatters light is colloid. Suspension can, but there's something that we need to do. Solution can never scatter light. So here we go. Let's start comparing between solution, colloid, and suspension. Solution is the homogeneous mixture. Colloid and suspension are both heterogeneous mixtures. Hetero mixtures. Now, in terms of particle size, we're talking about the solute for the solution. But for the colloid and suspension, yeah, we're talking about the solute. Let me just clarify it like that. So the solute, they're so small that are almost less than 1 nanometer in size. That's why you cannot see them with the eye. You need a microscope. However, the colloid, you can see the particles because it's a heterogeneous mixture, but the particles are not that large to be clearly separated from the solute and settle out in the mixture. Like, for example, when I mix sand with water, the sand particles are large, so they settle out, they precipitate. However, the colloid, they don't. So we say medium size and memorize the sizes. It's between 1 and 1000 nanometer. However, the suspension, they have the large size more than 1000 nanometer. Now, in the solution, we cannot see the solute. We cannot see it. It's a uniform, invisible, uniform solution. Now, the colloid, not very clear. It means I need to do a test in order to see the particles. It's not very clear to me if I can see it or not. And in the suspension, they're very visible. So with the eye, I can clearly, if I have three mixtures, I can clearly know that here's the suspension because I can see the particles. Now, filtration. Colloid and suspension, they can't be filtered. Can't be filtered. Can't be filtered. So you cannot separate the solute from the solvent because in the colloid, the solute is still small and it goes through the pores of the filter paper. However, in the suspension, you can separate it, can be separated by filtration. I can clearly separate the solute from the solvent. Separation upon standing. The suspension is the only one that has solid particles or that have the solute that is large enough to settle out. So separate upon standing, yes, because the particles are large enough to settle out. Settle out, I mean to deposit at the bottom of the beaker. Yani this is the beaker. You can see the particles settling out. However, for the solution and colloid, we cannot separate them upon standing. Yani the gravity effect doesn't separate the solute in the colloid and in the solution. So can't settle out. Remember the word can't settle out or can't precipitate. Okay, can't settle out, and I'm going to use the other word, can't precipitate. Okay, now the last one, the Tyndall effect. And I showed it to you in class. So if you refer back to the photos that we took in class, the Tyndall effect is a beam of light that you direct toward a mixture. Now, if the mixture is solution, you can see the light passing without any modification, as if there is nothing in front of that light. So, Tyndall effect, it doesn't show any Tyndall effect. However, if I have colloid, it's a different scenario. If I have a colloid, the light upon passing, you will see it inside the solution, scattered everywhere. You will see it. The particles, you will see light coming from the mixture. Okay? And when it comes scattered, the light. So I can see the particles inside the colloid when I direct the light on them. So we say, yes, it scatters light. It exhibits Tyndall effect. Now, the suspension. If I have a suspension, how does it happen? When I scatter, when I show the light. Now, suspension. If the suspension was left to settle, it means the particles of the gas are here. The particles of the solid, the making up the mixture. So when the light pass, it will pass clearly because it's going through the water and it's higher than the solid particles that are settled out. However, if the solution, the suspension mixture was mixed very well, and you are stirring it, you are mixing it, and the particles did not yet settle out, then you can see the beam of light and you can barely see light coming out from the solution. But this light will become stronger and stronger once the particles start settling out. So in the Tyndall effect for solution, for suspension, we say only if mixed and particles are not settled out. Or you can say sometimes it exhibits the Tyndall effect. If you don't want to explain this, you just say sometimes because it depends whether the mixture is mixed, stirred, or no. Moving on. Which pair of liquids is immiscible? And here, this is the point where you have to remember the mixtures that are the solvents that are polar and non-polar. In miscible and immiscible, we compare the polarity of the substances being mixed. If they have the same polarity, and I mean by that, if both of them are polar or both of them are non-polar, the liquids can mix. If not, they cannot mix. Yani one is polar, one is non-polar, they cannot mix. So, miscible are the liquids that are soluble in each other and can mix. Liquids that are soluble, soluble in each other and can mix. Miscible, I told you in class, like it's like mixable, miscible. Immiscible, it's the liquids that when mixed together, they always separate. They always separate, like the oil and the water. They always separate in two layers. In other words, can't mix. Okay? Now, for this reason, you need to know the polar solvents and the non-polar. There's a list. And whenever we do a mix from these two kinds, they're always immiscible. Or if I choose two options from non-polar or two options from polar, it will be a miscible mixture. So, what are the examples that I need you to know? In polar, first thing, the water is polar. The alcohol is polar, such as ethanol, anything that ends with "ol". The vinegar is polar. The acetone is polar. Okay? For the non-polar, remember those titles: oil, toluene, gasoline, carbon tetrachloride, carbon tetrachloride, um, okay, I'm giving you more benzene, um, I'm not sure if we're going to give more examples, but um, these are well known. Okay, a chloroform, yes, chloroform. So all of these are non-polar, and the rest are polar. Okay, so alcohol, ethanol, vinegar, um, uh, what else I can remember? Mm, I'm just thinking about acetone I mentioned. I want to give you examples that it comes in the quizzes. So I'm just trying to remember anything that can help. Glucose, maybe glucose syrup. Okay. Uh, yeah, I guess anything that ends with "ol", like for example, methanol. If they gave you methanol instead of ethanol, that's also alcohol. Yeah, the non-polar, sometimes I remember they gave once hexane. Hexane. It's a non-polar ether. You need those for the end of year exam. Okay. Type. The immiscible. Let's start. The immiscible are the one that can't mix. So alcohol and water, polar, polar, mix. Polar, polar, mix. Polar, polar, mix. Oil and water, non-polar. Here's the oil, here's the water. Non-polar and polar. So they can't mix. Now, moving on with our lesson, the next lesson is about calculating the concentration. Concentration is it's a measurement. It measures the amount of solute given in a certain solution or a solvent. So that's the concentration. So concentration, it's a measures the amount of solute in a given amount of solvent or solution. The concentration can be many types. Molarity and molality are both concentrations. Okay? So there are many forms of concentration. We just took the molarity and the molality. Now, the unit of molarity. When you have this, the formula is given to you in the exam. So the molarity is the mole over volume of solution. So the mole is in mole and the volume of the solution is in liter. Therefore, the unit is going to be mole per liter. Okay. Now, the molality is again mole of solute, but this time over mass of solvent in kilogram. So the mole again is in mole, and the mass of the solvent, like the mass of the water, is in kilogram. So the unit is mole per kilogram. So this one is for molality. Now, a definition. Whenever you are asked to write the definition, just go with the formula. So molarity, symbol is capital M, or I can also call it molar concentration, also called molar concentration. It is the amount of solute in moles per volume of solution in liter. So molarity, it's also called the molar concentration. It's the amount of solute in mole per volume of solution. Molality, I'm going to write it here. Molality, also called molar concentration. It is the amount of solid, the amount of solute, I can't say solid, of solute in mole per mass of solvent in kilogram. Okay, so here's the formula. Now, moving on with the calculations. Whenever you have questions of calculation, always write the given Write the formula clearly that you are using, substitute, put the answer and the unit. Never forget the unit. What is the molarity? Molarity is mole of solute over volume. And they've given me 0.5 mole solid sodium chloride in 200 milli solution. So that's the solute and it's given in mole. So there's nothing to do for it. And that's the solution given in milliliter. So I need to divide this by 1000. The 250 needs to be divided by 1000 and it becomes 0.25 liter. Remember, to go from milliliter to liter, we divide by 1000. The volume has to be in liter, as I mentioned now. So it is 0.25. So the answer is 2. 2 molar, or you can say 2 mole per liter. Hail M is the same as this one. Which of the following is required to calculate molality? If I want to calculate the molality, I need the mole of solute and I need the mass of solvent in kilogram. So volume of solution is needed for molarity. Mass of solute, I need to convert it to mole. Molar mass of the solvent not needed. Mass of the solvent in kilogram. Which of the following statement is true? Molarity, okay. Which one is affected by temperature? Let's explain this before we answer the question. The temperature, okay, let me put the formula first. Molarity is mole over volume. Molality is mole over mass. When temperature change, when temperature increase or decrease, mass can never change. It will not increase or decrease the mass because mass is the amount of matter contained in a substance. So when temperature increase or decrease, mass will never change. And therefore, molality, so therefore, molality is not affected. Who's affected? However, volume changes. If temperature increase or decrease, volume changes, and it changes in this way. Temperature increase, volume increase. That's what we're taking now in our lesson of gases. So um, if temperature increase, volume increase. If and vice versa. Let me just write and vice versa. And vice versa. Therefore, molarity is affected by temperature change. How? Molarity is affected by the temperature change. So, if volume of molarity, if the volume increased because temperature increased, therefore molarity is going to decrease and vice versa. So, if temperature increase, volume increase, molarity decreases. If temperature decrease, volume decrease, but molarity will increase. So here's the full explanation. So which of the following is true? Molarity changes with temperature, molality does not. Now, moving on, there are some questions that I'm giving here that summarizes the calculations that we need to do. I'll explain each one. 180 gram of barium chloride are dissolved. From the word are dissolved, I can understand that this is the solute. And I have a mass 180 gram. And whether it's molarity or molality, as I mentioned previously, I need to find the mole for both of them. So always remember that any given mass of solute, you need to use the formula of mole equal mass over molar mass in order to get the mole of solute. So before you continue the question, sort it out. Find the mole of the solute. So it's 180 given, 180 gram divided by the molar mass. And that is 0.865 mole. That's for the solute. Let's continue. Dissolved in water to form 500 milliliter of solution. So the volume of the solution given to me is 500 milliliter. Calculate the molar concentration. In the molar concentration, the solution needs to be in liter. So I always divide by 1000 if it was not given to me in liter. And now to calculate molarity, it is the mole over the volume. It is 0.865 over 0.5. And the answer is 1.73 mole per liter, or you can simply say capital M. Never forget the unit. Another example. Calculate molality. So I need the N solute and I need the mass of solvent to calculate molality. Now, of a solution made by dissolving 10 gram of the solute, and they've given me the molar mass. So, in order to find this, the mole of solute, it's equal to mass over molar mass. It is 10 gram over 74. So now I have the mole of the solute, which is 0.134 mole. Now they've given it to me in 100 grams of water. However, in the molality, I mentioned that the mass of the solvent must be in kilogram. So you need to divide the 100 grams by 1000 to convert it to kilogram. And that's a 0.1 kilogram solvent. Now the formula is ready to be used. Molality is mole over mass, 0.134 over 0.1. So the answer is 1.34 mole per kilogram. Another example. Calculate the molarity. Again, I need the molarity, which is mole over volume, of a 3-liter solution. So the volume given to me in liters. So the volume is correct. I'm okay with it. So the volume, there's no changes to the volume. Containing 4 gram of solute, molar mass is given. Okay. So the solute, I need to change the mass into molar mass. So it's 4 gram over the molar mass. Molar mass of Na 23O16H is 1. So let's find out the molar mass of NaOH. It's the molar mass of Na plus the molar mass of O plus the molar mass of H. All of these values are given. They might give it to you, you might get it from the periodic table, or in some questions, they solve the molar mass and give it back to you. Okay, so that is 40, if I'm not wrong, 50. 23 plus 16 plus 1, sorry, that's a 40 gram per mole. So 4 over 40, that's a 0.1 mole solute. And therefore 0.1 over the volume, that's a 0.033 mole per liter. Calculate the molality of 4 gram sodium hydroxide. I'm running late. I have another session that starts in few minutes, but I'll try my best. So just 3 pages left. So molality, again, I just used this 4 gram. So to calculate molality, it is mole of solute over mass of solvent. Probably it will be given to you like that in the exam, and over mass. So we just calculated the mole of solute, 4 gram. We're still in the same similar question. It is 0.1 over 500 milliliter of water. The density of water is 1 gram per milliliter. It means that every 1 milliliter water, they weigh 1 gram. So 2 milliliter of water weighs 2 gram. 100 milliliter of water weighs 100 grams. And now I have 500 milliliter of water. That's going to weigh 500 grams. In the exam, you need to mention this sentence. You need to say every 1 gram measures 1 milliliter, or you can highlight that the density of water is 1 gram per milliliter. So this 500 grams, 500 milliliter equal to 500 grams. However, the mass of the solvent must be in kilogram. So you divide by 1000 and the answer would be 0.5 kilogram. So 0.1 over 0.5, it is 0.2 mole per kilogram. Okay, just a second. Okay, now we continue. List the gas laws and the variables. So this is something that I would like to explain before I move on with the gas laws. We have Boyle's law, Charles' law, gay-lussac's law. We also have the combined gas law, and we have the ideal gas law and Avogadro's gas law, which are not given in your quiz, not included this time. However, we will mention these gas laws that I said now in other scenarios, in other revision sessions. Always remember this inverse triangle where you write P followed by V and T. Now, P, V, T, I need to talk about the variables. P is the pressure of the gas. V is the volume occupied by the gas. Could be in liter, could be in milliliter, it doesn't matter. Temperature is the temperature of the gas that always must be converted to Kelvin. If you want to use it in your calculations, you need to convert it to Kelvin. How is that? You add 273 to the given temperature in Celsius. Now, there's another variable, which is the mole, representing the amount of gas. But this one doesn't enter in the formulas yet. Now, Boyle's law. Boyle's law operate at constant temperature. So you hide the temperature and the formula will be between pressure and volume. So it's P1 V1 equal P2 V2. Let me just move this a bit. Charles' law is at constant pressure. So it's volume over temperature. V1 over T1 equal V2 over T2. Gay-Lussac's law is when the volume is constant and it's the pressure over temperature. Oops. Okay, so let me just erase this. It's the volume over the, it's the pressure over the temperature. Okay, now, again, what is the unit of temperature for the calculations using gas laws? Specifically, whenever I'm using Charles' law, because these two laws involve temperature, and Gay-Lussac's law, and the combined, because this involves temperature, temperature must be in Kelvin. Meaning, if a temperature in Celsius is given, you add it to 273 and it becomes in Kelvin. For example, a temperature of 10 degrees Celsius is given, so I add 273 to it, it becomes in Kelvin, etc. What is RTP and STP? RTP is the room temperature and pressure conditions. So RTP, I'm just gonna give you the wording of it, STP. So RTP is the room temperature and the pressure, and STP is the standard temperature and pressure. So the room temperature and pressure, and the room temperature is usually 25 degrees Celsius. You need to know this value, 25 degrees Celsius, and the pressure is 1 atmosphere. At this, or could be 298 Kelvin if it's given in Kelvin. At RTP conditions, the volume of gas is equal to 24 liter for every 1 mole. Every 1 mole of a gas will have a volume of 24 liter. However, STP is known as standard temperature and pressure, and at which the pressure is always 1 atmosphere. However, the temperature is 0 Celsius or 273 Kelvin, and the volume of gas at STP is equal to 22.4 liter every 1 mole. So basically, you need to memorize the conditions of STP, which are 1 atmosphere and 0 Celsius or 273 Kelvin, And RTP, it is 25 Celsius, which is 298 Kelvin, and the pressure of 1 atmosphere. Now, let's start with the practice questions. Identify the gas law for each given graph and explain the relationship between the variables. Let's start reading the question. If pressure increased to 4, so pressure is 4 atmosphere, what will be the new volume of the gas assuming the temperature is constant? So when they mention the constant, so they told me which one is constant. I go to my triangle PVT. They said temperature is constant. So you hide T. So your formula now is between P and V, which is Boyle's law. So we are in Boyle's law, which is P1 V1 equal P2 V2. Now here there's a graph given to me showing that P and V are inversely proportional. Inversely proportional. So if P decrease, V increase. So pressure is 4 atmosphere. So here's the pressure. Here's the 4 atmosphere. What will be the volume? The volume will be 2 liter. Okay? So here, there is no calculation in this question. It is just using the graph. So the volume will be 2 liter. So remember, this is the formula of the gas law. Okay. Next, a gas occupies a 300 milliliter at 20 degrees Celsius. If the temperature is increased to 80, what will be the new volume? So again, I'm talking about volume at a temperature. So V1 equals 300 milliliter and a temperature is 20 Celsius. If the temperature is increased to 80 degrees Celsius, what will be the new volume? Now, before we continue, I mentioned in class, immediately you add the 273 to the temperature. You do not continue until you put the temperature in Kelvin. So this is 293 Kelvin, and T2 is 273 plus 80. It is 353 Kelvin. So here's the triangle PVT. Nothing is mentioned about P. So the formula is Charles' law, showing a direct relationship between volume and temperature. It is V1 over T1 equal V2 over T2. So if we look at this one, for 300 milliliter, the temperature was 20 degrees Celsius. At 80 degrees Celsius, the volume is going to be 450. Or I can put it in the formula, 300 over 293 equal V2 over 353. Solving this, we get the volume as needed. So the answer is 450 milliliter. So V2 is 450 milliliters. Now, for the third question, I'm just gonna reply to my emails. Students waiting for me because I have another session. So the pressure of a gas is 1.5 atmosphere. So pressure is 1.5 atmosphere at 25 degrees Celsius. Before you continue, you add this one to 273 to convert it to Kelvin. That's a 298 Kelvin. Okay, so what will be the pressure at 100 degrees Celsius? So immediately the 100 degrees Celsius, you add 273 to it. So this is 373 Kelvin, assuming volume stays the same. So the volume is constant. So here on my triangle, P, V, and T, volume is constant. So this is gay-lussac's law, P1 over T1 equal P2 over T2. As you can see, so let me just substitute 1.5 over 298 equal P2 over 373. So for 1.5, I will do my calculations. 1.5 times 373. So the pressure is going to be 1.87 atmosphere. As you can see, these three laws, P and V, are the only one inversely proportional, whereas the volume and the temperature and the pressure and the temperature are directly proportional. And these graphs, you need to know how to draw them. Moving on. So, yalla, last page. Our student investigated the relationship between pressure and volume at constant amount of gas and constant temperature. You go directly to your graph, to the formula I told you. Temperature is constant, you hide it. So it is Boyle's law between P and V. Directly you will know the law. Anyway, if I look here, I see only P and V given. And when this is compressed, it means P increase. I can see that the size, the volume is less. Name the law demonstrated. That's Boyle's law. Sketch the graph that represents the relationship. So I'm going to do it over here. It is pressure versus volume. And it shows an inverse relationship. However, some students might write P, V and P still the same. You will still get the same shape. At 25 degrees Celsius, the temperature here is just a decoration for the question. We're not going to use it. It has a pressure of 2 atmosphere and a volume of 1 liter. So pressure 1, volume 1. If the volume is reduced to 0.6 liter, calculate the pressure. So P1 times V1 equal P2 times V2. And the pressure will be equal to, the new pressure will be equal to 3.3. Now, for the unit, the first pressure is given in ATM, which is atmosphere. So the unit is in atmosphere. Again, another question. If a pressure of the gas is doubled, so the pressure doubled, the volume of the gas will be halved because because pressure and volume are inversely proportional. If the pressure is tripled, the volume will be divided by 3, and so on. So the volume of the gas will be halved. Oh, it's a V. Which of the following is true about Charles' law? Charles' law, it is volume over temperature at constant pressure. So it occurs at constant pressure. Volume and temperature, like I showed you in the previous graph, they're directly proportional. So it is 1 and 2. Now some mixed practice for all the laws. For Boyle's law, always remember to use the unit. So volume is given 3 liter, pressure is 1.2 atmosphere. What will be the volume if the pressure is increased to 2 atmosphere? So V1 is 3 liter, P1 is 1.2 atmosphere, V2, P2 is 2 atmosphere. So P1 V1 equal P2 V2, 1.2 times 3 equals 2 times V2. Therefore, V2 is 1.2 times 3 over 2. That's a 1.8. Now, look at the unit. The volume is in liter, the first volume, so the unit will be in liter. Again, at constant temperature, so we are in Boyle's law, constant temperature. A gas occupies a volume of 2.5 liter, that's V1, with a pressure of 0.8 atmosphere, that's P1. So 0.8 and V1 2.5. What will be the volume? So they want the volume if the pressure is now 1.6. So 0.8 times 2.5 over 1.6. The V2 is 1.25, and you follow the unit. The first volume is given in liter, so you write it in liter. Charles' law. Again, a gas occupies a 2 liter, that's the volume, at a pressure of 0 Celsius, T1. Immediately I'll add to it 273. What is the volume? V2 when it is heated at T2 100 degrees Celsius plus 273, so that's a 373 Kelvin at constant pressure. In my triangle, PVT, constant pressure, so the formula is between V and T, Charles' law. So it is 2 over 273 equal V over 373. So times 2 over 273. The answer is V2 equal 2.73 liter. Next, a gas has a volume of 1.25 liter at temperature. Temperature, good, it's given in Kelvin. So 1.25 liter at a temperature 393 Kelvin. If the volume decreases to 1 liter, what is the final temperature in Kelvin, assuming that the pressure is constant? So again, we are in Charles' law. So V1 over T1 equal V2 over T2. So the answer is T2 is equal to 314.4 Kelvin. Last two questions. The gay-lussac. So I'm sorry, it's a long session. A gas has a pressure of 1.2 atmosphere at 20 Celsius, 27 Celsius. So pressure is 1.2 atmosphere and the temperature is 27 Celsius, which is plus 273. So that's a 300 Kelvin. What will be the pressure? Again, what will be the pressure if the temperature increased to 127? You immediately add to it 273. So 127 plus 273, that's a 400 Kelvin. Assuming volume constant. Here's my favorite triangle. P, V, T. They said volume constant. So my formula is P over T, P over T. So P1 over T1, P2 over T2. So 1.2 over 300 equal P2 over 400. So 1.2 times 400 over this. So the pressure is 1.6. Now, what's the unit? ATM. So you write ATM. Last question. A gas is sorted in a rigid container at a pressure of 2 atmosphere and the temperature is 50 Celsius. Immediately I'll change it to 200 I'll change it to Kelvin. So it is 323 Kelvin. What will be the new pressure if the temperature drops to negative 10 Celsius? Immediately I'll add 273. So that's a 263 Kelvin. So the formula is between P and T, P and T. So P and T, P and T. 2 over 323, P2 over 263. So 2 over. So the final pressure is 1.62 atm. Just like the given unit, you will find the pressure. And that's it.